Welcome back to The Deep Dive. Today, we're getting into something that I think frustrates pretty much everyone who uses a personal AI agent. I'm talking about the lag.
hmm
That infuriating pause after you ask it to do something even a little bit complex.
It's a real paradox, isn't it?
Yeah.
We give these agents incredibly powerful planning abilities through large language models, but those models are, well, they're slow.
How slow are we talking?
The research we looked at puts a number on it. Just to generate a multi-step plan, using something like the GPT-4 API, can take around 25 seconds.
25 seconds? I mean, in user experience terms, that's an eternity. That kills the whole experience.
It absolutely does. But what's really interesting is that the source material found a huge opportunity hidden in all this. They analyzed real-world data and found that about 30% of all requests, they're either identical or very, very similar.
30%. So a third of the time, we're basically asking the agent to resolve a problem it's already seen before.
Exactly. And that's a massive waste of resources.
Okay, so let's break that down. The standard workflow is pretty simple, right? A request comes in, the LLM makes a plan, some tools execute that plan, and you get a response.
Right.
So the obvious question is, why can't we just use caching? I mean, we've had that in computing for decades. Just save the final answer.
Because the similarity is in the task, not the final answer. And that's the key distinction. Traditional caching fails because two requests can have the same underlying steps, but completely different key details.
Ah, okay. Can you give us that travel example from the source? I think that makes it really clear.
Sure. So let's say request one is book a ticket from Hefei to Beijing for the day after tomorrow.
Okay.
And request two is book a ticket from Changsha to Shanghai for tomorrow. A simple cache would see those as, totally different strings of text.
Right, because the cities and dates are different.
Exactly. So it would trigger that slow 25-second planning process for both. But the actual plan needed is identical. Query the date, query flights, compare prices, and so on.
So the solution they came up with, this AgentReuse mechanism, it's about reusing the plan, not the final response.
Precisely. But that creates a couple of big challenges. First, how do you even tell that those two requests are similar if you can't just compare the text?
Right. How did they do it?
This is the clever part. It doesn't compare the raw text. Instead, it uses two steps. First, intent classification. It figures out what you're trying to do. Is this a book ticket task or a check weather task?
Okay, that makes sense.
Then it does parameter identification. It just pulls out those key variables, the origin, the destination, the time. It basically creates slots for them.
So it strips out the variables and then compares the skeleton of the request. It's comparing book a ticket from O2 with another book a ticket from
You
here.
got it. And that dramatically improves the accuracy of finding a plan it can reuse.
But that creates the second problem, right? You have this plan, which is probably just messy natural language from an LLM, and now you have to safely plug new information into it.
That's the other half of the puzzle. You can't just, find and replace words in a sentence without breaking the logic. So AgentReuse converts the LLM's plan into a clean, structured format.
Like a flowchart, almost.
Yeah, that's a good way to think about it. For each step, it defines the description, the inputs it needs, and, this is crucial, the dependencies between steps.
So the system knows exactly where Shanghai needs to go and that it has to happen before the price comparison step.
Exactly. It makes the parameter replacement safe and reliable.
So let's talk about the results, because when I saw the numbers, they were pretty staggering.
They really are. In their experiments on a real-world dataset, AgentReuse cut down latency by 93.12%.
93%. That 25-second wait just vanishes.
It pretty much does.
Yeah.
And that's because it works so well. They hit a 93% effective plan reuse rate. Their method for spotting similarities was just incredibly accurate.
I mean, that's a game changer. But there's always a cost. What's the overhead for running all this extra classification and structuring?
That's what's so compelling. The cost is tiny. It adds about 100 megabytes of extra VRAM and less than 10 milliseconds of latency to each request.
So a 10 millisecond cost to save 25 seconds.
It's an easy trade-off to make. It more than pays for itself.
So we've cracked the code for speeding up single, simple tasks like booking a flight. But the source has hinted that this is just the beginning. There's a bigger challenge on the horizon.
There is. All of this work is focused on single intent requests. The real next frontier for making agents truly autonomous is handling complex, multi-intent requests that have causal links.
What do you mean by that?
Well, think about a request like this. If the indoor temperature goes above 28 degrees Celsius, then turn the air conditioner on and set it to 26 degrees.
Ah, that's not just one command, it's a conditional rule, an if-then statement.
Exactly. How do you classify that? How do you create a reusable plan for a condition that might not even be triggered for hours? That shift to multi-intent classification is the next big problem to solve.
And that's definitely something to think about until our next deep dive.